Here we're integrating x times the square root of 1 minus x to the fourth from 0 to 1. We were also given two hints. First, we should make an appropriate substitution. And then second, instead of anti-differentiating, we should interpret this integral as the area under a curve. Well, let's start by figuring out what the appropriate substitution. So typically when we do use substitution, we look for composite functions and we let u be the inner function. So here we would let u be 1 minus x to the fourth. So du would be negative 4 x to the cubed dx. Now when I go back and I look at this integral, I don't have an x cubed. I have an x. So we could try to do some finagling, but I think it's just going to end up being more complicated. So the real problem here is that I want this x and this dx to be absorbed by the substitution that I make. So for this problem, we just have to be a little bit more clever than simply picking the inside function. So what I'm going to do is I'm going to let u be x squared. Now, it seems like a funny choice. There's no x squared in that original integral. But we could think about it as the integral from 0 to 1 of x times the square root of 1 minus x squared squared dx. And now, when I'm thinking about that innermost function, I see an x squared right there. So when u is x squared, du is 2x dx. And my original integral does have an x and a dx right there. It doesn't have a 2, so I'll divide both sides by 2. And I'll obtain 1/2 du is equal to x dx. Making those appropriate replacements right there, we get the integral. The x and the dx get absorbed into the 1/2 du, so we have a 1/2. And we have a square root of 1 minus u squared times du. Next, we need to figure out what our limits of integration are. So when x is 0, u is equal to 0 squared, so u is 0. So the lower limit is 0. The upper limit, I want to figure out what happens to u when x is 1. When x is 1, u is 1 squared. So u is in fact 1. So there we go. My upper limit is a 1. And we have the integral. That 1/2 is a constant coefficient. We can take it outside of the integral. Then we have the integral from 0 to 1 of the square root of 1 minus u squared du. So far, that looks like a pretty good substitution because it is an easier integral. Again, it's still too complicated or to just anti-differentiate as is. And u substitution also isn't going to be helpful here. So this is where that second hint comes to play. And I want to be able to think about this in terms of area. So if I were to let y be the square root of 1 minus u squared, then I would see that y squared is 1 minus u squared. And so y squared plus u squared is equal to 1. And that equation should ring a bell. And we should know what it looks like. So if I have my y-axis here and my u-axis here, then the equation y squared plus u squared equals 1 graphs a circle of radius 1. That's my circle, and its radius is 1. And now I'm looking at just the positive part of the circle because I have the positive square root. It's not plus or minus, I just have the positive. So my graph looks like that. Now I'm integrating from 0 to 1. So I want this area right here, from u equals 0 to u equals 1. Well, that is in fact just the quarter of a circle of radius 1, and the area of a circle is pi r squared. We have a quarter of it, so we're going to have a quarter pi r squared. Our radius is 1, so my area is pi over 4. So this integral is going to be 1/2 times pi over 4, or pi over 8. It's very handy to keep in mind what these integrals are doing. They're not finding the antiderivative and plugging in the endpoints is a way of computing the integral. But when I think about geometrically, what it means is it's the area under the curve. So when we were trying to find the integral from 0 to 1 of the square root of 1 minus u squared, I was precisely trying to find the area of that curve right there. And that's how we obtained our answer.